Hi, welcome to the Shiko Math Lab Fun Probability Problem Solving sections here. Today, we are going to talk about one very classical problem here. So the problems tell you, say here, if I have two random variables, x and y, and the x has a Poisson distribution with the parameter alpha, and the y has a Poisson distribution with a parameter lambda. And there are two independent random variables here. So now I define the new random variable z is equal to the x plus y. So what will be the probability mass function of z here? That's what we are interested to find. So in this video, I'm going to show you by using two methods to find it. So the first method here I'm going to show you is using the moment generating functions, MGF method. And then the second one is here, we're going to take a look at the same problem and by using the variables transformation methods here. So of course, we expect them to get the same answers, right? All right, so if you like this video, and please feel free to subscribe to the channel. And also, if you have another interested way to solve it, and then maybe you can drop me a message and we can take a look also. Okay, so now let's go ahead and get it started here. All right, so let me go to the whiteboard and let's go get it started. All right, like I said, I'm going to solve this problem by using the two methods here. So the first method is going to be the moment generating functions methods here. All right, so the z, okay, so the method number one, I'm going to use the MGF methods here, right? So z is the new variable we defined as the adding these two random variables, x, y. So we know the MGF, right? So MGF of the z's here, based on the moment generating function definition, will be the expected value e to the what? E to the tz, right? And then in here, we can just easily to write e to the t. So what is z here? Is x plus 1, x plus y here, right? And then we can use the exponents property. So this will be to the e, the tx times e to the ty. Also, then we can break it to here. So it will be the e to the tx times e to the ty. Correct? So from here to here, why? Is because we assume the x, y, they are independent, right? So those are the independent random variables. So that's why we can break it. And now, after you break it, then you notice this is the definition for what? You know, this is a definition for the moment generating function for the x, and this is the definition for the moment generating function for the y's here. So if you go to find the moment generating functions of the of the Poisson, so I know the ETX, the moment generating function here will be exponents. Then because the x is the alphas, right? So the x is the alpha. So this will be the alpha, then the e, the t minus 1. Okay, so then the ety is the definition of the moment generating function for y. So what is the moment generating function here? Will be the exponents. Lambda is e to the lambda e to t minus 1 here. Then because this is the e function, so we can combine that. So it will be the alpha, the et minus 1 plus the lambda, the et minus 1, right? Then easily you can combine it. So what you do here, you factor out the ET minus 1 here. So this one will be the alpha plus lambda and the E, the T minus 1. And then we know there's a very important theory about the moment generating function. So we know the moment generating function unique decide what is the random variable for here. So this one's here, right? So this one's here. What is this? This is the moment generating functions here, right? So what is the moment generating function of the Poisson with the parameters alpha plus lambda. So I know in here, so that's why, so the Z will be the Poisson distribution with alpha plus lambda. Okay, so this is what we called by using the moment generating function. It's pretty easy, right? Okay, so now let's also take a look at how do I do it if, like we say, hey, can you solve it, by using the variable transformation? I say, okay, let's go ahead and start, right? So this is the by using the variable transformation methods here. All right, so because the X and the Y, since the X and the Y are independent, right? So now we can say that we can put the joint PDF of X, Y here. Because the independent, it will just be you multiply the PDF for each one here. So this is X is alpha, so it's alpha to X e to the negative alpha, right? And then times Y factorial, and then this is lambda to the Y e to the negative what? E to the lambda. So let's combine a little bit. So this will be the X factorial, Y factorial, then E I can combine with alpha plus lambdas, right? Okay, then I have the alpha x lambda y here. Okay, so of course here we know x is from the 0, 1, 2, da da da, and the y is from the 0, 1, 2, 3, da 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 here. Okay, so now, okay, so we still define this new random variable z equal to the x plus y. Okay, so now I can say here, so I say x is equal to the z minus y here. Okay, so now I can replace my joint function of x, y. I can replace it to be a function is a joint function for the y and the z's, right? So it's y and the z. So I just replace the x equal to the z minus 1. Okay, so now let's go ahead and take a look at x is equal to the z minus y here. So it's z minus y to the factorial, y factorial, then e to the negative alpha plus lambda. Then this is e to the z minus y and times lambda y. And in here, this is we know the dx dz here is 1, right? So this is what? This is like our Jacobian. So that's why you can times 1 here. So basically, I just try to replace the transformation back to disjointed PDF. And don't forget, always check your Jacobian to see is 1 or not. Okay, after that, I want to find the z's, right? So since I want to find the z, so what does that mean? And that z is my marginal distributions, right? So what I need to do, I need to add what? I need to add up the y's here. All right, so that's why I need to add up the y. So it's a summation y from 0 to the z here. And then here, this will be the z minus y factorial, y factorial, okay? And Okay, so then here the top here is e to the negative alpha plus lambda, then the e, the z minus y, and the lambda y here. Okay, so one thing here, be very careful, is here I'm adding y is from 0 to z because z is equal to the x plus y. Both x and y are like from 0 and the 1, 2, 3 is a positives, right? So y, the maximum number the y can add to is z. See here, right? So this is very important. See here. Okay, after that, all right, so the next thing is here, I'm going to do is, because I'm a summation of the y, so let me take all the variable has nothing to do the y outside to simplify here. So this is alpha plus lambda. This parameter has nothing to do with the y here, right? So now here, this is a summation, y from 0 to z, and so this is z minus y factorial, okay? And then here I have a lambda y, okay? So the things I have remaining is lambda y e to the z minus y here. Okay, so the next step is a pretty important step here. So the next thing here, because I look, you look at this z minus y and the y factorial, it's very similar like the coefficient of the binomial expansion. So I said, well, how about if in here I have a z factorial here? All right. So of course you cannot just arbitrary add z factorial. So what do you need to do here? I need to divide by what? I need to divide by z factorials here. Okay. So now take a look this. All right. So take a look at this things here. I'm going to put this ones here. So I use the color coding here. So y equal to 0 to the z here, right? So this is the z factorial, and then this is z minus y factorial, and this is y factorial, and this is lambda y, and this is e to the what? Z minus y here. All right, so this is the lambda y, and okay, so this is sorry here. This is alpha. I don't know why we put the. So this is the alpha. Okay, so this is the alpha z minus y. So here. Okay, so yeah, careless mistake here. So this is the alpha z minus y here. All right, so here, don't know why I put another z here. Okay, let's just correct that. That is alpha. And so here, the same things here. Just need to be extremely careful. So this is alpha z minus 1. Okay, so now this is alpha z minus y here. Okay, so if you take a look, what is this things here? This one here is just what is the combination z to the y's, right? So the distance here will just change to the summation y from 0 to z, c the zy, lambda y, and the alpha z minus y's here. So what is this? This is the binomial expansion. So what is this one going to become to? So this one will become to here, right? So this will become to like these numbers here, the alpha and the lambdas here. So that's why this one will become to the alpha plus lambda to the what? To the z's power, right? So this is what we call is the binomial expansion. Okay, so now I can put it back to here. So this one's here. So this is e to the negative alpha plus lambda. Then this is z factorial. And just like we get from this red ones here, this is alpha plus lambda to the z here. Wow, so this is the what? So this is the probability mass function of the what? Of a Poisson with what parameter? Alpha plus lambdas here. Okay, so this, you can use this is what we call the variable transformation methods here. Like I said, the key things here is you need to recognize to use this binomial expansions, right? So then you will be able to get the same things here. So of course, the same as the moment generating functions there. Okay, that's it. So it's a very interesting problem. You can approach by two different methods here. All right, so if you like it please feel free and to subscribe the channel, or if you have any questions, please send me a message and I'll be glad to answer that. Okay, have a good day and talk to you in my next videos here. Okay, bye-bye.